In today's section, we're going to find or continue to find the volume of a figure, but instead of revolving it about one of the axes, we're going to revolve it about a line. So what is that going to look like? Well, if you looked at the animation portion of this, we took a figure with the x-axis there, or the y with the y and x-axis, but then we changed that axis of revolution to maybe a y equals -3. How would I find the volume of this figure if we revolved it around this line? Well, notice we could create this equation, which was y equals 0. We can give this an equation of maybe 16 minus x squared, the square root of that. If I were to move all of this up 3 units, then this y equals -3 would become that the axis x equals 0. We could also move these two equations up, so we get the square root of 16 minus x squared plus 3. In this equation, y equals 3. Then it becomes a problem where we revolve it around the x-axis. So what does that kind of look like? Well, our volume is going to be the integration from a to b of that top curve, but we have to be careful when we say top curve because depending on the orientation of the graph, we're going to call more of the outside curve. So we're going to do outside minus that axis of revolution. So if I take that outside curve, which is the square root of 16 minus x squared, subtract off of it a -3, I actually get the square root of 16 minus x squared plus 3. And if I square that, that'll give me the volume of that entire figure. And what I would do from that is subtract the inside figure, or the inside equation, minus that axis of revolution. So I do the inside function minus my axis of revolution squared dx. Likewise, I can go around a vertical line, in which case we'd have pi times the integration from a to b of, again, the outside minus the inside. But here we'd have maybe an f of y minus the axis squared minus the inside maybe would be a g of y minus the axis squared dy. So we have to make sure that we are in the variable of y. If we go around a vertical line, if we go around a horizontal line, it's in the terms of x. So in example 1, let's go ahead and look at a function, x squared plus 3. So that function is going to come in here, a nice diagonal. It's going to go through the point here, 3. G of x equals 2, so that's going to be a horizontal line through here. G of x equals 2. I'm going to go ahead and label those so I can know what I'm working with. I'm going to revolve it around the line y equals 1. Well, in this case, if I were to subtract 1 from each of these equations, that axis of revolution would become the x-axis. And it becomes a problem where we revolve two functions around the x-axis. So how do I get them to do that? Well, I simply subtract 1 from each of those functions. So my volume becomes pi times the integration. I go from 0 here, and in this case, I got to figure out this point of intersection. Well, that point of intersection we should see as being 1. Again, you can put that in your calculator if you need to. But we go from the integration from 0 to 1 of my outside curve this time is going to be negative x plus 3 minus the axis of revolution, in this case, which is 1 squared. That gives us the big area, or the big volume, big figure. I'm going to subtract out of it this inside piece in here. And to find that, I'm going to revolve my g of x, which is 2, minus that axis of revolution, which is 1 squared dx. I can clean this up a little bit before I throw it into the calculator. So I get negative x plus 2 quantity squared minus 1 squared dx. So I go ahead and pull out my calculator, do my pi, then our math 9, we're going from 0 to 1 of that quantity, negative x plus 2 and quantity squared minus 1 dx. Go ahead and calculate that, and we end up with 4.1887, or round it 4.189. I have only one other example I want to show, and that's if we revolve it around one of those vertical lines. So here we're taking f of x equals x squared, which is going to look something like this, a nice parabolic function. Go ahead and label that. Our g of x equals 1. I'm going to kind of exaggerate where 1 is there. So there's our g of x equals 1. So here's our figure that we've got. And then what we need to do then is revolve it around this x equals 2 line. Well, if that's going to be 1, we're going to revolve it out here at x equals 2. Now, how do I find then that volume? Well, my outside curve in this case is going to be this part of the parabola. We can go ahead and label it as out. And then the inside part is going to be this part over here. Well, remember, if we're going to revolve it around a vertical line, then we had to be in terms of x. So we know that y equaled x squared. So we know that x has to equal plus or minus the square root of y. Well, how does that play into this parabola? Well, we know that this part here is the negative part, and this here is going to be the positive part. So here we're going to have x equals the negative square root of y, and here x is going to equal the positive square root of y. Again, it's not going to be a major issue with this as we go in squaring it out. However, our volume is going to equal what is this point here. Well, if we go around y equals, we know this point here is 1 and this point here is 0. So we're going to take the integration, or pi times the integration from 0 to 1 of my outside curve, which is negative y, minus the axis of revolution, so minus 2 squared. And from that, we're going to subtract the positive version of this, which is the square root of y minus 2 squared dy. And again, we can go ahead and throw this into our calculator. We're going to do our pi times the integration. And we're going to go from 0 to 1 of the negative square root of x. Remember, we can go ahead and leave that as the negative. I don't know if I put a negative in there. Yep, negative square root of x. And then minus 2 and that quantity squared. And from that, we're going to subtract the inside part of that, which is the square root. We need a quantity square root of x minus 2 and our quantity squared dx. And getting that value, it's going to take a little bit of time, asking it to do a lot. We end up with a volume of 16.755. And that's going to be the figure here revolved around that x equals 2 line. And that's an example of one where we revolve it around a vertical line or we revolve it around a horizontal line.